Hello, this is the Project 3, or Lab 3, Part 3, 2D viscous flow simulation over a flat plate at an AOA of 10 degrees. First, we're going to start with Fluent, pop open that geometry. Ideally, you should already have the wind tunnel from the last lab. Then you could just add a flat plate inside, keeping in mind the blockage ratio of 10% and the height, given that the front and the back of the point is what you're going to use to calculate that. I'm just importing mine. I already did it earlier, just saving time. But here it is. Small flat plate with negligible height. Once you do that, you could just back on out. And then go into your mesh. Give it a second to load. All right. Wait for the model to pop up. Here we are. Let's go back to our z-axis and work on naming our selections. Grab all of your exterior wall, the top and the bottom of the exterior walls, not including the inlet and the outlet. Then named selection should be 6 edges, or how many edges you have. I have 6. We're going to name this walls. Nice and simple. Now we're going to do another name selection for our inlet. There we go. Name this inlet. Over here, we're going to do another named selection for, you guessed it, outlet. Go inside. We have one more name selection to do. It's going to be the individual walls of our plate. Reason you do the individual walls is it just will be easier to see all the calculations later. I'm going to do top face. Bottom face. Front face. And as you could expect, rear face. All right. Once all of that is done, we're going to work on our mesh. To do this, we're going to make an inflation. This is going to apply a nice boundary layer on our plate so we can see how forces are accurate against it. Just select your geometry as the whole face, and then for the boundary, just select all the walls. It's going to be a little tricky because of the side walls. Bam, there you go. Apply it. Astonishing. You'll see how that affects it later. We're going to go into mesh, make our method. The geometry is the surface. I like to do triangles. Now we're going to edit our mesh example. We're going to go down. I'm going to do 0.003. You could go lower if you want something more accurate, or you could stay high and then it'll run faster. But as you go lower, it's going to be a lot slower. So just keep that in mind. Once you do that, generate, see how it looks. Make sure it's not strange. Beautiful. And see, this is what we did with the inflation. You see these nice specific layers on the outside so we can get an accurate measurement of what's going on the outside of the plate. But overall, that is the mesh of the tube and plate done. You can now close out, and let's move on to setup. Oh, first of all, update. Might have messed up because I clicked the upstream components, but just update the mesh again normally. This is going to take a bit. Just going to make sure it updates properly. Okay, it did. Now you can move on to setup. We're going to be doing a 2D sim with double precision, and everything else is fine. Start your sim, give it a minute. Once you see your model pop up, give it a couple more seconds, and then you should be good to go. It's building, so it's close to being done, and there we go. You can see your inlet, you can see your outlet, all is good. We're going to start with general. There's nothing to change in general, you're all good there. Open up model, let's go to viscous since this is a viscous flow. If you were doing inviscid, just turn it on right there. Do K epsilon because it's better. Standard, standard. And then everything is fine. Everything is off unless specified, but for the sake of this project, everything else should be off. So, should be done with models. Checking over. Yep. Let's move on to materials. Fluid, then you can go air if you have a ridiculously high density or changing your density. Or if there's a specific constant viscosity, you can change that here. Otherwise, you can leave it as the basic. Shouldn't change your calculations too much. Now we're going to move on to your boundary conditions. For me, the velocity inlet was already made, so you don't have to worry about that. If not, you could just select it, set it as the inlet. Using the lab from lab 2, you can get the, you should have your velocity inlet already calculated. Since this is for 60 hertz, it should be about 3.80417. And then apply that. Apply it again just to make sure. Outlet, you shouldn't have to do anything. Internal, you don't have to do anything. And same thing with the walls. These are all fine. Reference frame is fine too. Named expressions is fine. Move on to methods. This is all fine. You can try it in simple if things aren't working, but generally the base settings is pretty alright. You have to adjust control or report definitions. More monitors. Let's initialize our program. Your first 10, no issues. Let's go to run calculations. We are going to set, I'm going to set 800 iterations. You can go higher if you want to be accurate, or you can go lower. Actually, I'm going to do 700 for the sake of time. I go higher for more accurate, lower for faster, but for the sake of time, I'm just going to do 700. It should solve it out before that. Yeah, okay, there you go. If you're running it on base settings and it goes over like 300, something's probably wrong. But now that we have our results, let's get our pressures. That'll be done in that'll be done in graphics, contours. you're going to do calculate static pressure, static pressure, and then you're just going to select everything. Should be no issue. Compute, save, display, and there you go. Take a picture of this, put in your files, amazing stuff. Save display again. Make a new contour. This one is going to be dynamic pressure. Dynamic pressure, select all the faces. You could just click the first one, then shift left click the bottom one. Boom, that would be your dynamic pressure. You have a high pressure zone on top and low pressure in the wake, as you'd expect. It's actually a negative pressure zone in the wake. And now we're going to make one last contour for pressure, which will be, you guessed it, total pressure. Which in our normal wind tunnel, there's no change, but because we have something that produces drag, you're actually going to see there is a change in the total pressure due to drag making a wake zone that has a low pressure wake zone. So that is the contours. To get the other, actually, before we leave in the reports, you can go to forces, and then you can calculate the forces against the walls. If you do it with the x being 1, print it. Here will be your drag force, and then the coefficient of drag here. If you go 1, then 0, and then print it, these will be your lift force. So there's the lift force, and then there's the lift coefficient. Back out, go out of here. And we're going to switch to results to get the velocity contours and vector. So let's edit our results. Here we are. Do a contour, contour velocity, location. You're going to want to do symmetry 1 for velocity, range global. Set this to a nice number of about 100. Apply it. Pretty simple stuff, honestly. There's your velocity contours. For later sake, we're going to want to set the transparency to something like 0.5. You will see why in a second, because now we're going to add the vectors for velocity. Go in here. Location, symmetry 1 again. All of, we're going to do what is it? Sampling, do equally spaced. You're going to want to set this to a crazy number if you're doing the whole wind tunnel. So let's do like 2000 symbol, switch to Aero 2D, and then crank this number down. Apply it. And there's your velocity contours with vectors. Close those out. Press this to activate, to turn on streamlines. You're going to want to do 3D streamlines. Start from the inlet, equally spaced. We'll do about 80. Velocity forward, no issue. Apply it. And then there's your streamlines.